Hi everyone, let's talk about a step discontinuity in a parallel plate waveguide. In particular, this is going to be an introduction to a technique known as mode matching. So the basic problem is I have essentially two waveguides here, right? So here is waveguide region 1, and over here we'll call this waveguide region 2 here. And you notice I have what's called a step discontinuity, right? So you imagine this kind of going on forever in that opposite direction, and all of a sudden it reaches this point where the waveguide suddenly opens up and then wants to keep on going out this way. So the question for this is, how do I calculate the total electric field in a situation like this? And all right, so let's just kind of define the geometry here. So this I'm going to define as z equals 0. We have a height over here. So I'm going to, from here to here, this is some height h1. And then up over here is going to be another height, like so. I'm going to call that h2. All right, h2. And I'm going to have an offset down here, which I'm going to denote as y sub 0. Okay, so this is, in this case, you can see how y sub 0 is a negative value, right? So if we continue this on here, this would be y equals 0, right? So this is a negative offset. And in this particular case, you notice it's called an open waveguide. And there's a bunch of different permutations here, right? So for example, I could have a large waveguide constrict into a small one. So that'd be a constricted waveguide. Small to big would be an open waveguide. You can also have offsets, okay? So this would be like a negative offset here. And then this would be, say, a positive offset. So the way you solve them is all slightly differently. You have to kind of account for the geometry. So we're just going to focus on the open waveguide here to introduce the basic technique. So what I'm going to imagine is I know that there is some wave, electromagnetic wave, exciting this from the left. And we're going to assume a TE polarization while we're at it here, right? So that means this is y and this is z, and x is coming out here. So technically, the x goes into the paper here, right? So it's x cross, how did that, sorry, yeah, x cross y. Am I getting that right? So if z is positive this way, and this is y, so y is that way. So yes, x cross y. So positive x is into the page there. Right-hand rule there, okay? But that's okay. So just remember, x will come into and out of the page. Doesn't matter which particular direction is which. So I'm just going to assume I know that there is some field coming in here from the left, some field profile. It's going to strike this boundary here, and two things are going to happen. One, there's going to be some transmission of field into the target region here, and then there's going to be some reflection of energy back into the incident region over here. So let's just write out the general form for these fields here. Okay, so I'm going to write E sub x I, so that's the incident field, and since we're TE polarization, that is going to imply it has an x component here. And this is going to be a function of y comma z, and it's just a Fourier series like we already knew from long ago. So it's going to be a summation from n equals 1 to infinity, a sub n times sine of gamma sub n y e to the minus j beta sub n z. Remember, this is just the general solution to any arbitrary field profile propagating down a parallel plate waveguide. Okay, so for the sake of argument, we're going to say I am exciting this from the left, and so I know what this profile is. Or another way you can say it is I know what all of these little coefficients are, right? So remember, gamma sub n was n pi over h1. Okay, so h1 over here. And then you had, there was a k naught, which was omega over the phase velocity. So we'd say omega over c. So there's no dielectrics here. So everything's propagating at the speed of light. And then we also had beta sub n is equal to the square root of k naught squared minus gamma sub n squared, right? So that was our dispersion relation there. Okay, so that should all just be reviewed. Nothing new has happened yet. We're now going to say, okay, what happens when some energy wants to reflect here? So I'm going to write this down here. E sub x r for the reflected electric field as a function of y comma z is equal to the summation from n equals 1 to infinity I'm going to write this as a B sub n, so not to be confused with beta here. And it's going to have exactly the same form, just that sign is going to change to indicate that they're propagating in the other direction. So e to the plus j beta sub n z. Okay, so the only thing is I don't know what these coefficients are. All I know is this is the general form that whatever is reflecting here, it has to satisfy that general form for its function, right? Now, finally, there's also going to be some transmitted field over here. So I'm going to write this as E sub x t for the transmitted field into the target region. Let's say y comma z. And this is going to be a little different because we have a different height here, h2, and we have this offset. So we also have to account for that in our terms. So it's going to say the summation from, and I have to give this different letters because I don't want these indices to kind of get confused with each other. So I'm going to call this m equals 1 to infinity. And c sub m, sine of gamma sub m, I'm going to put a little prime here because I need this gamma to be different from that gamma there because it's going to be, that should be h1, not hi. So it's going to be n pi over h2 rather than n pi over h1. So I'm going to denote that with this little pi here. And my axes, my coordinates have shifted a little bit. So I'm going to get y minus y naught, and then e to the minus j beta sub m prime z here. Okay, so again, this is the general solution for some wave propagating down a parallel plate waveguide. And all I had to change was some of these little parameters here, right? So gamma sub m prime is going to be m pi over h2 now. And then my k naught hasn't changed. It's still the same frequency and phase velocity. And this beta is now going to follow a similar expression here. So what has this gained? Well, all I've done is write down the general form for these functions. I don't know anything about how they relate to each other yet. All I know is that whatever is propagating in here and here, it must follow this general shape, okay, or this functional form here. So how do we relate these expressions to each other? Well, this is where we get this notion, what's called mode matching here. Right, and that name will become clear in a little bit. So what you have to remember, though, is I need to enforce a boundary condition here. Because what's going to happen is all of these fields are going to kind of add up here at this point, and they have to be continuous here, okay? So what we're going to write is the first boundary condition is the electric field across this little border here. So I'm going to do, oops, sorry. So this little border here at z equals 0, the electric fields have to be continuous there. So what I'll write that out is, I'm going to say the electric field Ex of y comma z minus, it's 0 minus, is equal to E sub x of y comma 0 plus for this little region here. For, we'll say 0 is less than or equal to y, which is less than or equal to h1. And 0 otherwise, right? Because I have this metal wall here, okay? So all the fields in my transmitted field, they're going to add up to whatever is, they're going to be something here, and then they have to go down to 0 over here, okay? And then I'm going to have another boundary condition. So let's kind of scooch this here. Technically, it's the magnetic field is also going to have to be continuous. But it turns out mathematically, because there's no dielectrics or anything, there's a much simpler way to impose that boundary condition. And that is the partial derivative of my E sub x with respect to z at 0 minus is equal to my partial derivative with respect to z at 0 plus. Okay, so the normal derivative is going to have to be continuous as well. So you notice what we have is if the function is continuous, then the tangential derivative will also be continuous by default. But I need my derivatives in the normal direction here to also be continuous. Again, this isn't necessarily always true. Like if I add dielectrics or magnetic materials, then this is a slightly different boundary condition. But for simplicity, you can treat this as such when there are no dielectrics here. Okay, so let's go ahead and impose those conditions right now. Okay, so let's go ahead with our first boundary condition. So what we're going to do is let z equal 0. And remember, just the fields on the left have to add up to the fields on the right and then be 0 along the walls in the target region. So we're going to write something like the following. The summation from m equals 1 to infinity of c sub m sine of gamma sub m prime y minus y sub 0. Close parentheses. So I put in a 0 for z, so this little term went away. And this is going to equal, and I have to split it up like the following. I'm going to get the following. N equals 1 to infinity. And I'm going to have the incident and the reflected fields on top of each other. They just add together at this point. So what you'll get is a sub n plus b sub n sine of gamma sub n y. And this is for 0 is less than or equal to y, which is less than or equal to h1. So what I've just said here is that in the left, I have the incident plus the reflected fields just superimposing on top of each other. And I put in a value of z equals 0, and everything is going to be continuous from here to here. But now I have to also account for this little wall here. So what I'm going to also have is 0. So you see it's a piecewise function. And this is for y naught less than or equal to y, which is less than or equal to 0. So that is the little bottom wall here. And then I also have to include the top wall. So I will have h1 is less than or equal to y, which is less than or equal to h2. Okay, so this is my continuity condition. And it looks kind of horrible, but it is trackable. There's going to be a simple trick to kind of get around this. But first, let's go ahead and write out our second boundary condition. And so again, it's just we're going to calculate the derivatives with respect to z on the left and right, and then we're going to add them all up and equate them. Okay, so if you just go ahead and do that, it's pretty straightforward to show. You'll get, again, the summation from m equals 1 to infinity. And notice I'm using m over here and n over here because I don't want them to kind of get crisscrossed. They're sort of slightly different here, okay? So if I take the derivative with respect to z, I'll get a j beta sub m prime coming down in front of all of these terms in this summation. And then this term will again go to 1 when I let z equal 0. But that j term is actually going to disappear because I'm going to get a j on both my incident and reflected there. So if you channel away all the negative j's and such, you'll get essentially beta sub m prime times c sub m sine of gamma sub m prime y minus y 0. And that is going to equal... now what's interesting is that derivative only needs to be continuous across this little zone here. The derivatives can actually do whatever it wants on this wall because the normal component of an electric field, or sorry, the derivative of the electric field here, the E field has to be 0. The tangential E is 0, but the derivative of it can kind of do what it wants here. So what you'll get is then the summation from n equals 1 to infinity, and then I'll get a sub n minus b, that's a b sub n, beta sub n, sine of gamma sub n y. And this is going to be from 0 less than or equal to y, which is less than or equal to h1. So those are my two boundary conditions. Again, this is just saying the electric field has to be continuous across that little aperture and then 0 on the wall. And this is saying the derivative, my normal derivative of my electric field is going to be continuous across the little aperture, but then kind of do whatever it wants along the walls. Anyway. Okay, so that looks like a lot because you notice I have like infinitely many equations with I have two equations here with infinite unknowns, right? So I'm assuming that these A's here, this is a given, but I don't know what the B's are here, and I don't know what the C's are over here. Okay, so I have infinitely many of these and infinitely many of these, and I only have two gigantic nasty equations to kind of relate the two. Now, in practice, when you actually do a computation, we're going to not necessarily have infinitely many terms in our Fourier series. So eventually we're going to truncate this series to some finite value. So for what it's worth, let's just go ahead, instead of having infinity, I'm just going to put in an n here like this, okay? And instead of being equals, I'm just going to kind of put in approximately, right? So that approximation will get better and better as I make n approach infinity, but I will never actually be truly exact. So we're just going to kind of impose that condition now, because sooner or later I'm going to have to put this on a computer. So in this sense, you notice I have basically two equations, but there are n unknowns here and another n unknowns over here. So I have two n unknowns. But the accuracy is n should approach infinity. Ideally, okay, I can never truly get to infinity in a real calculation, but ideally I want this to be a very, very large number. But I still have 2n of these unknown coefficients to solve for. So the question now is, how do I unpack this mess? So this is where the essence of mode matching kind of comes into play. So what we're going to do is I'm going to start up here. I'm going to multiply this by a sine of gamma something something in both sides, and then I'm going to do an integration. Because remember, we have that problem of orthogonality, okay? And that's going to save us from this infinite mess of equations. So let's come down here. I'm going to do the following. I'm going to say the summation from m equals 1 to n, c sub m sine of gamma sub m prime y minus y naught. I'm going to multiply it by sine of gamma k prime y minus y naught, like that. And then I'm going to integrate from y0 to y0 plus h2. Okay. So in other words, I'm multiplying it by this term, and I'm going to do the integral from bottom to top here. Which, if you look at that, this, and then of course 2 over h2 there out in the front to normalize everything. This is equal to c sub k. So in other words, if I multiply both sides of this and then I perform this integral, all of the terms in this summation are going to vanish except for the kth term. So what you'll get, this is going to equal, so I got to do it again on the other side here. So c sub k is equal to, and so let's do it like this. I'm going to get summation from n equals 1 to n, a sub n plus b sub n, sine of gamma sub n y, and I'm going to multiply this guy here, sine of gamma sub k prime times y minus y naught, or sorry, don't forget the dy there, dy. There's going to be a 2 over h2, and I'm going to integrate from, technically I need to integrate from y naught to y naught plus h2. So for simplicity, it helps to just give this a shorthand, y0 to say y1. I'm going to let that equal this little guy here. Or I guess technically, y naught plus h2, is that? Oh, that's right, sorry. So I'm going to call that y naught is equal to, or y1 is y naught plus h2, like that. And technically this is a piecewise with the 0, but this 0 actually is going to annihilate this integral from the limits, because remember, it's 0 from here to here and then 0 from there to there. So I can actually, the integral itself is going to be 0 everywhere except these limits here. So what you can actually do on the right hand side is cross that out. That goes from 0, and then that goes to h1, because it's the integrand will be 0 everywhere else on these two bits here. Okay, so that kind of looks horrible, but let's rewrite this a bit. So I have c sub k is going to equal the summation from n equals 1 to n. I'm going to factor this out, a sub n plus b sub n, like that. And then I'm going to get a 2 over h2 times the integral from 0 to h1. And then I'm going to get sine of gamma sub n y times sine of gamma sub k prime y minus y naught dy, like that. Okay, so why did I separate all that? So all this stuff out here is just some coefficients. This giant mess here has a closed form solution. You can grind on the calculus and crank out a closed form solution for this entire mess right here. So this entire thing, I'm just going to give it a name. This is an integral. It has a solution. There's some functional. You can grind that and write a function in MATLAB that grinds it out. I'm just going to call this something like I sub, let's see, Kn. I'm going to put a prime there to kind of indicate it's for the second region there, okay? So if we then rewrite all that one more time, I'm going to put it up over here. C sub k is just the summation from n equals 1 to n, a sub n plus b sub n. And then I'm going to have this I sub, and instead of k now, it's going to make a little more sense to just change this index back to m. I'm going to put mn prime like that. Okay. So I want to go back to m and n as my index because it's going to be a little more intuitive when we start writing this out later on here. So I could have called this k and n or k and l or whatever, but m and n is going to make a little more sense. Okay, so you notice what happened by exploiting orthogonality. This infinite series got ground down to a single term as a function of this whole thing here. So I have now this you can think about is technically n equations, right? Because I can repeat this calculation for all terms in this series up here, for all m. So I can go from 1 to n, and I have an equation that will relate my mth transmission coefficient here to this little integration over here. So this, you can think of this as a shorthand, that this is actually n equations, right? Because I can just repeat this from m equals 1 to n. Okay, and I'll get n equations out. So this thing is known, and I have n unknowns here, but this is n equations to my 2n unknowns. So you can kind of see what just happened here. So let's now, what helps is to introduce a slightly different notation now. Okay, so let's rewrite this back over here. You have c sub m is equal to the summation from n equals 1 to big N. A sub n plus b sub n, I sub m n prime. What I'm going to do is define a vector c, where it's just going to be c1, c2, c3, dot, 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 all the way out to c sub n, and transpose to make it a column vector. And then I'm going to define another vector a, likewise, is going to be, a1, dot, 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 a n, transpose. And then b is equal to b1, comma, dot, 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 b sub n transpose. Okay, so you can kind of see where this is going because I'm going to now express this as a matrix vector equation up here. And this I sub mn here, I'm going to define a matrix M2, again, to indicate because we're in region 2 here where this is kind of being integrated here. Where the rows and columns here correspond to I sub mn prime, that integral. So each element in this matrix is going to be the solution to this little integral over here. All right, so you write a function that grinds on this integral here and gives you some sort of solution, and you just fill this matrix with those elements there. And what you get is an equation that basically looks like this. C is equal to m2 times a plus b, like that. So by writing it in this notation now, you can see a lot of the complexity starts getting buried and vanishing here. Because I have essentially now, this is one unknown vector here, and this is another, UNK for unknown. This is another unknown vector over here. So I have one equation now with two unknowns. Okay, by expressing these as vectors, that 50 unknowns has been now encapsulated down to just 2. Okay, so I have one equation with 2 unknowns. I just need another equation of this kind of form, and I can then presumably calculate these b's and c's here. Okay, so what you do is we come back. Where's our equation? So we're going to do that same idea on this equation here. So this matrix vector equation represents the continuity of the electric field in this giant mess over here by applying mode orthogonality. And I wish there was a name for this. I like to call this the mode overlap matrix, or this is the mode overlap integral, because you kind of see how I have these modes and I'm kind of integrating their sort of overlap on each other there. So I think that's a cool name for that. So we're going to do another kind of similar analysis for this equation here. So instead of multiplying by some sort of sign here, we have to do, turns out you have to use this term over here. So what I'm going to do is pick out another k value, multiply here and integrate and do the same to the left side. So what you'll get is something kind of like the following. So I'm going to start by putting this, or flip-flopping them and doing it from left to right here. So we'll have the term on the left, the summation from n equals 1 to big N. And I'll have a sub n minus b sub n. And there's going to be a beta sub n times sine of gamma sub n y. And I'm just going to multiply by sine of gamma sub k y, say, which we'll turn that, oops, excuse me. So I multiplied this little term here, and we're going to eventually turn that k into an m again. So it's just an arbitrary placeholder. And then we're going to do the integration from 0 to h1 of 2 over h1 dy. And you can see what's going to happen is this integral is going to kind of come over here. All these terms factor out, and I'm going to get that delta function again. So that is going to evaluate to, what do we get? We've got a sub k minus b sub k times beta sub k. So that orthogonality is turned to this summation. I plucked out just the kth one here. And now I got to do the same thing to my other side of my equation over here. So what I will then get is this is all equal to, I will have the summation from m equals 1 to n. I'll have a c sub m beta sub m prime. And then we'll get 2 over h1 times the integral from 0 to h1. You'll have a sine of gamma sub m prime, y minus y naught, sine of, so just bear with me, gamma sub k y dy. So you see I get this mode overlap integral once again. The only difference here is that instead of dividing by an h2, I have to divide by the h1, but it has exactly the same functional form. It's just those terms have been flip-flopped. So I'm going to call this I sub kn, and it'll leave off the prime. And you can kind of, these i's are basically the same. Again, the only difference is that little division over there. So there you go. And again, oops, sorry, that's an n. And we're going to eventually turn that into an mn when we replace the k's and whatnot there, okay? So let's write that out. So what you'll have, we'll just kind of put it all together back up here. I'll have a sub k minus b sub k beta, or sorry, we don't want k anymore. I'm going to put back the m's now, and then do some little rearranging on my indices here. So I have a sub m minus b sub m times beta sub m is equal to the summation from n equals 1 to, big N. And I will have c sub, n beta sub n prime times I sub mn, like that. So whether you want to call this one the prime or not is not that big a deal. And so again, this is a kind of matrix vector equation again, but I have these betas in here. So in this sense, it helps to define a matrix. I'm going to call this D, like a diagonal matrix, where the diagonal elements are going to be, say, beta 1, beta 2, ... to beta n, like that. And then a similar one here, a d prime. And then this whole thing finally simplifies. I'll get something like this, a minus b, and I think, you put a d here, that diagonal matrix goes there. This is equal to, then you're going to get, I'm going to call that d1, or call it d, say, and then I'll have a d prime, or you could call it d1 and d2, that works too, times c, this is going to be my m1 times c, like that. Is that right? Did I get all that right? Yes. Okay, sorry. So that was a little messy, but we'll clean that up in a second here. So you notice this is another matrix vector equation. It's a little messy. I kind of made a little mistake there. But you see I've got D1 and D2. And if I used better foresight, I probably could have given these better names here to make more sense. But I have two matrix vector equations with two unknown vectors. So in a sense, it's two equations now with two unknowns. So all you have to do now is put these together. And so we're going to rewrite these just a little bit so that it makes a little bit more sense. So I'm going to have the following. I'm going to write M2 times A is equal to C minus M2B. So I just rearranged this guy here, and I'm going to rearrange this one as well. And you'll get D1A is equal to D2M1C. So these are matrix plus D1B. Sorry for the smudge there. Okay, so you notice this over here, this is known. This is my given here, and these are my unknowns over here. And so what you can do is I can create a matrix vector equation out of matrices and vectors. You can actually so it's called a block matrix vector equation. But basically you have negative M2, that's a matrix. Then there's going to be an identity matrix over here. And then this guy is going to be a D1, and then I'll have a D2M1. Then this is going to be B and C, like that. So you notice if I do it follows the same rules. Even though they're matrices and vectors, they still follow the same rules for matrix vector multiplication, right? And you can build this giant matrix, this block matrix in MATLAB very, very easily. You just add matrices within matrices. And then this is going to equal the following. M2A, and then D1A over here, like that. So if you then invert this matrix, you can calculate all of your B's and C's in one little fell swoop. And I will now have essentially the solution to, where's my original? I now have essentially the solution to all of the electric fields everywhere in space. And if I know all the electric fields, I will also know all of the magnetic fields, and you have a solution. Okay, so it's a little complicated. The tough part is you got to calculate this guy here, but it's pretty straightforward. You do some calculus, you can grind on that and write a function for it. So that will fill all of your M matrices here. Then you have these diagonals here, which just contain all of the longitudinal propagation constants. And you just fill up this block matrix equation here. And you get just a giant vector of unknowns, and you just kind of post-process it all. You get all of your coefficients back, and then you can use them to just calculate the total electric field everywhere. Okay, so that is the essence of the mode matching technique, because you can see how we essentially had this discontinuity here, and we matched, quote unquote, the modes on the left and right side, and then imposed those boundary conditions there. Okay, so that is the mode matching technique for calculating a step discontinuity in a parallel plate waveguide. And you can kind of see how there's a lot of value in this sort of thing as well, because hypothetically an interesting problem, you can use more or less the same techniques, would be something like this. Suppose I have an aperture here and I'm exciting it this way with some radiation, and I want to know how much energy gets coupled in. This same sort of thinking will tell you how to solve for a problem that looks like this. So there's a whole bunch of different variations you can solve using this sort of thinking. Another really fun one would be something like this, where you can have, here's a waveguide, and then you put in a little aperture like this. So again, you kind of match the modes on the left and the right, and you can calculate something, right? So this is PEC up here, PEC down here, and just this sort of squished aperture here, right? So all sorts of fun stuff. And this idea also will translate into 3 dimensions. So you can do this with full-on rectangular waveguides. Of course, the math really explodes if you do that. But it's the same notion. So this is a very powerful mathematical technique, if you can kind of wrap your brain around it, that allows you to do all sorts of interesting stuff in very complicated geometries. And in fact, you can even do like cascades of this stuff too, right? I could have mode matching here, and then I could put a constriction, say, over here, and then you would just have a transmission and then a reflection there, and you just match everything again, and you can calculate the whole kind of system there as well. So lots of power in this method to do very complicated problems, and you get infinitely arbitrary precision just by adding more and more terms to these vectors, right? So normally you'd pick like, a few dozen terms here, but you can just crank it up to, 5 trillion if you really wanted to, and you'll let your computer grind out and you'll get just as much perfect precision as you want just by adding more terms to those series. Okay, so there you have it. That is the mode matching method in a nutshell. And there are some textbooks on this. If anyone's interested, I can give you some references. You're not necessarily expected to replicate this yourself, but it's good to know that this exists, that it is a powerful tool, and some of you may find use for it in the future in your careers. So there you go.